All right, so if we want to analyze each one of these types of optical devices, whether it's a lens or a mirror, first of all, a quick look at the shape. In order to make a converging mirror, if you want the rays of light to hit the mirror and bounce off and converge together, what sort of shape would that have to be? Would you expect that to be convex or concave? Let's try convex and see what happens. So if you've got a mirror shaped like, let me make that thicker actually. Let's say this is the shape of the mirror. And if we have an object on, let's say, this side, when we say convex, it means it's sort of bulging outwards. So if the side of the mirror that's relevant to the object is bulging outwards, then what's going to happen to a ray of light that comes in, let's say, like this? What would you expect to happen to that ray of light? And would that bend upwards or downwards? Take a look at the normal line, though. If we draw in the normal line here, yeah, if we draw in the normal line, let's say this is our normal line. It's not quite perpendicular, but maybe something more like that. So here's the normal line. The ray of light is going to have to deflect, making the same angle with the normal line. So it's going to bounce off something like this, so that these two angles are the same. So this ray of light bounces off like this, making the same angle with the normal line. It can't deflect downwards because then the angle with the normal line would be much larger, so that doesn't make sense. So that means that the rays of light, and also like if we put one here, it's going to bounce off. In this case, the optical axis itself is the normal line, bounces off to make the same angle. And note that these rays of light started off getting kind of further apart, and they end up getting even more further apart. So this mirror is not making the light converge. This mirror is actually making the light diverge. So this convex shape would be a diverging mirror. So a convex shape, if the object is on the convex side of the mirror, then that's actually a diverging mirror. So let me put this over here. To get a converging mirror, we're going to actually need a concave shape. So let me draw the same shape, but let's look at the opposite side of it. So exact same shape of mirror, exact same portion of a sphere. Let me draw that a little more accurately. Something like that. But now let's put the object on the other side of it, on the concave side. Maybe here. Oh, also we're going to need a focal point. If you imagine that mirror as a portion of a sphere, the focal point is going to be on the side of that halfway towards the center. So presumably this is a portion of some sort of sphere. Let's say the focal point is right here. And let's say the same for this one. Let me tidy that up a little bit. Okay, so let's try both of these cases. Just to list out what types of rays we can draw in. If you have a mirror that is concave in shape, so the concave side is where the object and light are, that's going to be a converging mirror. So let's take a look at what that does to the rays of light. You could, for instance, have a ray of light that starts off parallel to the axis, hits the mirror, and what's going to happen to it? Yeah, that'll bounce off going through the focal point. Or what other ray could we draw in here? Yeah, a ray of light that goes through the focal point and bounces off, exactly, bounces off to become parallel to the central axis. And that's actually enough because we can now see a point where those two rays intersect. So we could certainly say the image is going to be at that location. If we want to be absolutely sure, we could draw in one more, maybe a ray from the object towards the center of the mirror, the center of the surface, where the optical axis hits the surface, and it'll bounce off, making the same angle. So you should get symmetry here. These two angles should be the same. Let me actually draw those in. Specifically, this angle and this angle have to be the same angle. But that should all intersect in the same place. So that location would be the image. So image looks like it is upside down, further back than the object is, and larger than the object. And what kind of image would we call that if the rays actually intersect at that point? Yeah, that'll be a real image because the rays really intersected there. However, it's also possible to get a virtual image from this converging concave mirror. And how would you do that? Yeah, we'd have to place the object on the, I would say this is already behind the focal point. We'd have to, in the sense that it's, well, let's say further away from the mirror than the focal point is. If we were to move the object so that it's inside the focal distance, if it's so close to the mirror that it's closer than the focal point, closer to the mirror than the focal point is, that would create a virtual image because of the way the ray tracing would work out. So the converging mirror, the concave shape, can create a real image or a virtual image. And that's depending on whether the object is further out than the focal point or closer in than the focal point. Or alternatively, what happens if you put the object on the focal point? Yeah, that's going to create no image at all. Because if you put the object on the focal point and try drawing out the ray tracing, the reflected rays end up being parallel to each other. So they never meet on that side. And if you backtrace them, they'll never meet on the other side either. So it's possible for a converging mirror with concave shape to create no image if the object is at the focal point. So those are all the possibilities for the converging mirror. Also, if we try the same for the diverging mirror, actually first, are there any questions on the converging mirror before we take a look at the diverging mirror? So for the diverging mirror, the critical thing here is where we put the object. The object is on the side of the mirror opposite to where the focal point is. In that case, we could still draw in, for instance, a ray of light parallel to the central axis. But what's going to happen to that when it hits the mirror? That's going to bounce off in what sort of way? Yeah, it's going to bounce off upwards. And specifically, we could draw in a normal line if we have a perfectly accurate picture of the spherical surface. But as a shortcut, if you know where the focal point is, I mean, really the whole point is if you know where the focus is, then you can draw these rays much more easily. If you draw in a line through the focal point and through that intersection where the ray hits the mirror, the important thing about the focal point is that any ray of light that comes in parallel is going to bounce off to become collinear with the focal point. So that's going to bounce off along this path. And this looks like it's something very different for the converging versus diverging mirror. Converging mirror, you've got a ray that starts parallel and bounces off to go through the focal point. Diverging mirror, you've got a ray of light that starts parallel and bounces off away from the focal point. But the thing is, in both cases, you've got a ray of light that starts parallel and becomes on the same line as the focal point. It becomes collinear with the focal point. So in this case, these are both really doing the same thing. A ray of light that starts off parallel to the central axis, bounces off along a path that is collinear with the focal point. It's just that that's on opposite sides of the mirror. Collinear in the sense that it goes through the focal point versus collinear in the sense that it's going away from the focal point. Because it's still on the same line, but direction matters. Any questions on that so far? And then for the next ray, we can also do mostly the same thing. For the converging mirror, concave in shape, a ray of light that started off collinear with the focal point bounces off to become parallel. We can do essentially the same thing here. We can say that if we have a line between the object and the focal point, any ray of light that starts off collinear with the focal point should bounce off to become parallel. In this case, we have a ray of light that starts off going towards the focal point, but of course it never actually gets there this time because the mirror is in the way. So that just bounces off to become parallel. So those would be the equivalent principal rays for this diverging mirror. And of course, as usual, we can also draw one that starts off going towards where the central axis intersects the mirror and bounces off to make the exact same angle. That can be kind of difficult to draw because you've got to sort of either use a protractor to get it right or eyeball the angles and make them close enough. But that looks probably close enough. Also, if you have a location of the center of the sphere, because this mirror is supposed to be spherical in shape, if you know where the center is, and where should we expect the center to be? If you know where the mirror is and you know where the focal point is, where should the center be? Yeah, 2 times the focal length. Because the focal point is supposed to be halfway between the center of the sphere, this hypothetical sphere that the mirror is part of. So the center should be twice as far away as the focal point is. So this should be the center of the sphere itself, somewhere around there. So that means that we should be able to draw a ray from the object straight towards the location of the center. Again, we can draw out these straight lines as sort of a framework. Any ray of light going straight towards the center, how should that bounce off? If it's going towards the true center of the sphere. If it's truly going straight towards the center, that's a radial vector, a radial line. So it should hit the sphere surface at a right angle. Anytime you've got a ray of light hitting a surface perpendicular, yeah, exactly, it's going to bounce straight back the way it came. In fact, we could do that with this one also. If we mark the converging mirror, if we were to mark the center twice as far back as the focal point, let's say right about here, any ray of light that is collinear with the center, and of course here it's kind of off screen, but a ray of light that's heading that direction, if that were to hit the mirror, like if the mirror were actually large enough for it to hit, it would bounce straight back. And I didn't draw this exactly accurately, but it should hit that same point. So that's another ray you can draw in. If you know where the center of the sphere is, which you can always get by just doubling the focal length, then you can draw a ray of light that's collinear, a ray of light from the object that's collinear with the center, that's going to bounce straight back the way it came. Any questions on those mirrors so far? And it looks like these final rays of light aren't actually going to intersect over here. So what would we have to do instead? Since they're never going to meet on this side, how do we find the image? Yeah, we trace them back. We backtrace. So ignoring everything that happened before the mirror, just backtrace these. Let me make that a little thicker. Backtrace all of these final rays of light. And we can say they all seem to have come from this one point. So that one point where they all seem to have come from is what type of image? Yeah, that would be a virtual image because, I mean, it's an image because they seem to have come from that point. It's virtual because they never actually passed through that point. So that would be the location of the virtual image. Virtual image right here. And notice that that is right side up, and in this case, smaller than the original object. With convex mirrors, if an object is inverted, yeah, the important thing is a virtual image is the same orientation as the original object. A real image is flipped compared to the original object. So it's not so much that a virtual image is always above the axis. It's that the virtual image is the same orientation as the original object, just a different size perhaps. Whereas a real image is always going to be flipped compared to the original object. Any questions on that so far? And if you move the object around, you're going to get changes to where the image is, but it's still going to be a virtual image. Because remember, for the converging mirror, if you move the object around, at what point does the image suddenly switch from real image to no image to virtual image? What's the change point there? Like if I have a virtual image, yeah, as I'm moving this, it's virtual image, virtual image, virtual image, and then suddenly no image at all, and then switches to a real image, or other way around, sorry, real image, no image, virtual image. So you get that sudden change when you cross over the focal point. But for the convex mirror, the diverging mirror, as you move the object around, you're never going to cross over the focal point because the focal point's on the other side of the mirror. So that means you don't get a sudden change if you move the object around on the diverging mirror, the convex side. So that means the diverging mirror is always going to create a virtual image. Any questions on that so far? And you can use the lens and mirror equation, 1 over f equals 1 over o plus 1 over I for both of these. But mathematically, how do you distinguish between these? How can you tell, or how can the equation tell the difference? How do you tell the equation that you're using a converging mirror versus a diverging mirror? Yeah, for the concave converging mirror, you'd have a positive value for the focal length. And by the way, I wouldn't write that as plus f. I would write that as say what you know about f. F is greater than 0. Whereas for the diverging convex mirror, we would treat the focal length as negative. F is less than 0. Would that make C, what is C here? Is that the curvature or something? Radius, I think we would still treat radius as a positive number because radius is just the distance from center to surface. So I think radius would be treated as a positive number either way. I guess it depends on what equations you're using it for. And yeah, I would say the radius of the sphere is twice the absolute value of the focal length. So we probably want to write that as C equals 2 times absolute value of f. There may be some equations where the radius of curvature shows up where it does matter what sign it is, but I'm not sure if that would actually matter or not. But geometrically, we treat radius as a positive value anyway. One useful way to remember this, though, let me actually tidy up this diagram a little bit. Those back traces are getting kind of cluttered. One useful way to remember this, though, at least for mirrors, this doesn't work so well for lenses, but in general, for both the focal length for mirrors and also for the image distance for both mirrors and lenses, positive is the direction light is traveling. Let me actually write that down in the middle because I think this is very important. Positive is the direction light is traveling. So this is true. I'm putting this in the middle because this is true for the lens, all the lenses and all the mirrors. Positive for the image distance anyway is the direction that light is traveling at the end. For example, on this mirror, we've got an object on the left side. Light starts off traveling to the right, but then it bounces off to the left. At the end, light is traveling to the left. So we treat to the left as the positive direction. That means an image on that side, for instance, this real image here is on that positive side, on the side that the light is traveling on at the end. So we would call that image distance positive. That is, I is going to be a positive number, that distance. Also, the focal point is on that side that light is traveling at the end, so we treat the focal length as a positive value. For the diverging mirror, in this case, and whether it's left or right or up or down or whatever, just depends on how you arrange it, how you orient the mirror. So don't get too attached to thinking of it in terms of left or right or whatever. It's just the direction light is traveling is the important direction. In this case, we've got an object here. Light starts off traveling to the left, bounces off, and is now traveling to the right. So the final rays of light are traveling to the right, so we're going to treat to the right as the positive direction in this case. The focal length, though, is on the other side of the mirror from the direction light is traveling at the end, so that's why we treat this focal length as negative. Also, this image, specifically a virtual image, is on the back side of the mirror, the side that light is not traveling on. So that's why we treat this image distance as a negative value. Image distance for a virtual image is less than 0. Any questions on that so far? Or any other questions on the mirrors in general? Then let's explore lenses. To get a converging lens, what shape do you have to have a converging lens? Other way around, actually. You got to have bending sort of outwards. And this is actually one of the instances where mirrors and lenses kind of behave in opposite ways. Generally, we're still building these from surfaces of spheres, like a converging or diverging mirror. You just take a sphere covered in shiny material and slice off a section of it. For a lens, it's not quite as simple as just slicing off a section of a sphere. It's still talking about spheres, but it's more of an intersection of spheres. If you take like a sphere and then another identical sphere and shift them, sort of a Venn diagram type shape, and then you take the intersection of those spheres. Let me try drawing this out. So this region here, yeah. So this is how you create a lens shape. the lens is just the overlap of those two spheres. And lens actually comes from the same root word as lentil. The original meaning of lens was just a lump of glass shaped like a lentil. So that shape, if you send in rays of light there, and note that both surfaces are portions of different spheres. If you send in a ray of light here, it's going to refract through the lens. For instance, if you send in a ray of light, a thinner ray of light so we can see what's going on, send in a ray of light parallel to the central axis, it's going to bend. And if you actually set up the normal line here, we're going from, let's say, fast to slow, from air to glass. So it's going to refract. And if we take a look at the normal line there, let's say here's the normal line. Since we're going from fast to slow, we're decreasing the speed. So what's going to happen to the angle? Instead of going straight through, it's going to bend so that what happens? Would you expect that to bend to make the angle bigger or make the angle smaller? In general, the way refraction works, if you got this ray of light coming in and making some original angle with the normal line, if you're going from fast to slow, the speed has decreased, and that makes the angle decrease also. So the ray of light is going to bend to make the angle smaller. Something like that. We've gone from this large angle to a much smaller angle with the normal line. So we have the ray of light coming in, it bends to make the angle smaller, and now it hits this other side. So we're going to draw in another normal line. Normal line at this location. And it originally makes this angle with the normal line. But now we're going from slow to fast. So what has happened to the speed if we're going from glass to air? Yeah, the speed has increased, so that means the angle increases also. And I usually look at this, exactly, it should move away from the normal. I usually think of this as, imagine it goes in a straight line. It's not going to go in a straight line, of course, but imagine for the moment that the ray of light just continues in a straight line. If it did, it would make the same angle with the normal. But we don't want the same angle. Since we're going from slow to fast, the speed has increased, so the angle should also increase. It's going to bend to make a larger angle on this side. So this is the path light is going to take through this lens. It starts out like this, in this direction, parallel to the axis. It's going to bend this way and then bend this way again. And this is going to be true for any ray of light. Let's say we have another ray of light that starts off parallel to the axis. That's going to bend towards the normal, or sorry, no, yeah, towards the normal in this case, and then away from the new normal. And it's going to go like that. In fact, any ray of light, and I'm just eyeballing it here rather than drawing out the normal vectors, but the important thing is that these rays of light that start off parallel to the central axis are all going to bend towards this one point. And what do we call that one point? If all these rays that started parallel get bent towards one point, exactly, that is the focal point for this converging lens. And we call it a converging lens because all these rays of light that started parallel end up converging towards each other. So this is a converging lens, and its shape is convex. This is one of the things where mirrors and lenses don't really match. If you have a mirror that's got a concave shape, then its behavior is converging. If you've got a lens with a convex shape, then its behavior is converging. So the concave and convex is referring to the shape of the lens or mirror. Converging or diverging is referring to what it does to light. And I think the converging versus diverging is really a much more important thing to look at because that's describing the behavior that we actually care about. What happens to rays of light? So that'll be the focal point. But since as opposed to a mirror, like a mirror, light comes in and bounces off. So you really only have one side that you care about. But for the lens, light can go through, and it can go through in either direction. So we could also have, for instance, rays of light coming in from the other side. Those are also going to bend and converge on a focal point on the other side. So you could have rays of light going through on both sides, and that means you have a focal point on both sides. So a lens, since it's symmetric and can have light going through in either direction, is going to have a focal point on both sides, and that should be equidistant on both sides. So that converging lens has two focal points, not just one. They should be the same distance from on both sides from the lens itself. Any questions on that so far? Now, the problem with this sort of diagram is that drawing out the actual shape of the lens can be kind of tedious, and it tends to make the diagram get really cluttered, drawing out what's going on inside the lens. So what we usually do is we just treat the lens as so thin, so flat, that we can ignore its thickness. We're going to pretend that its thickness is so small that it basically rounds off to zero. So instead of drawing it as the actual shape, we're going to draw it as essentially just a single vertical line. So here is the lens. Of course, in order to, we also need a way to determine, is it converging or diverging? So the usual style we do that with is we draw little end caps. So these end caps curving inwards, these don't mean the lens is actually shaped like that. This is just shorthand for this lens is converging. Versus for a diverging lens, we're going to draw sort of outward bending end caps. Again, this doesn't mean the lens is actually shaped like that. It's referring to the behavior, what it does to light. So a diverging lens, which is typically concave in shape, is going to have the opposite effect. Any rays of light that come in parallel are going to diverge away from each other, and they're specifically going to diverge outwards from a single point. If you've got a ray of light coming in, let me make that smaller, ray of light coming in, it's going to bend outwards. Another ray of light coming in also bends outwards. All these rays of light coming in to a diverging lens are going to bend in the outwards direction. But not just all over the place. They're specifically bending away from a single point. If you backtrace these rays that started parallel, you'll find a single point that they all seem to come from. And that single point is called the focal point. So that's what a focal point means for a diverging lens. If you've got parallel rays coming into the lens, they're going to hit the lens and they're all going to bend outwards away from some single point on the backside that we call the focal point. Any questions on that so far? So let's try out some ray tracing. Let me just say we have some focal points here. Oh, and also the lenses follow the same naming convention as mirrors as far as the focal length is concerned. For the converging lens, the focal length is going to be treated as positive, even though it shows up on both sides. And for the diverging lens, the focal length is treated as a negative number, even though it shows up on both sides. So in those cases, it's not so much about which side it's on, because the lens has focal point on both sides. The positive and negative here for the focal length is largely about making sure that the thin lens, thin mirror equation still works. In a way, you could sort of say the thin lens equation is set up for working with a converging lens or a converging mirror. But if you treat diverging as having a negative focal length, then the same equation still works. Any questions on that so far? So let's say we have a focal point on both sides of this. Let's say we know where the focal point is. And let me double check to make sure that's the same length, just for reference. Pretty close, but I can make that more accurate. Okay, and let's go ahead and assume this one has the same focal length. Okay, so that distance would be called f, and it will be treated as a positive value for the converging lens and negative value for the diverging lens. But let's try some quick ray tracing just to see what things look like. Let's say we have an object here. We're going to have some rays of light. And for the lens, if you have a ray of light from the object going straight towards the center, what's going to happen to that? Any ray of light going straight towards the center of the lens is going to do what? If it was a mirror, it would bounce back. But since it's a lens, it doesn't go back. It goes... yeah, it's going to go through. Any ray of light going towards a lens is going to go through. It's just going to bend. Unless it's going straight towards the center, then it has no bending at all. It's just going to continue in the exact same direction. So that's one ray of light you can draw out for either lens, whether it's a converging lens or a diverging lens. You can draw in a ray of light straight towards the center, from the object straight towards the center, that just keeps going straight through. The other principal rays that are easy to draw in for a lens, or for a converging lens specifically, and compare this as we do this to what happens with the mirror. For the mirror, we had a ray of light that started off going parallel. So let's try that same thing. A ray of light that starts from the object that starts off parallel to the central axis. And what's going to happen to that as it passes through? That's going to bend in what way? What happened to the ray that starts off parallel and hits the mirror? Yeah, just like the converging mirror had a ray that started off parallel and bounced back towards the focal point. The ray of light that starts off parallel to the optical axis and hits a converging lens is going to bend to go through that focal point on the other side. And notice that we're already seeing that these rays are going to pass through this one single point here. So that's where the image is going to be. But to be sure about that, let's draw in one more. In the same way that for the converging mirror, a ray of light through the focal point hits the mirror and bounces off to become parallel. For the converging lens, a ray of light that starts off through this near focal point, that is the focal point on the same side as the lens that the object is, that's going to go through but bend to become parallel to the optical axis. So we keep those bent rays going until they meet. And of course, they're going to continue past that point. But the point where they meet, anybody standing beyond that point is going to think, oh, those rays came from this point. So that point is where the image is going to be. And what kind of image is that? If the rays of light actually meet there, that image is, yeah, that is a real image, which means the image distance should be treated as what sort of value? Should that be positive? Or yeah, it should be positive. And so but whether you're dealing with a mirror or a lens, a real image is going to have a positive value for I. And this also goes back to this core idea that positive is the direction light is traveling at the end. Light from this object travels and hits the lens, but we don't really care about that. The important thing is the light after the lens, since the light travels through the lens and keeps going, this direction is the direction we're calling positive, because that's the direction light is traveling at the end. So any image on that side is, of course, going to be a real image because that's where the light is. So that will be a positive value for I. And a converging lens, much like a converging mirror, can produce real or virtual images depending on where the object is. If you try putting the object on the focal point, once again, you get no image. If you put the object inside the focal length, too close to the mirror, you get a virtual image. So try that on your own. Try drawing out the ray tracing for an object at various different locations compared to a converging lens and see what happens. Any other questions on the converging lens? Then let's take a quick look at the diverging lens to finish this off. Let's say we have an object here, and we're going to draw in some rays. The rays for the diverging lens can be kind of confusing at first, but they follow a very similar pattern to the converging lens in terms of where they're going, but also compared to the diverging mirror as well. One ray we can always draw in, as before, is a ray from the object that goes through the center and just keeps going in a straight line. But let's take a look at the other principal rays. A ray that starts off parallel. For the converging lens, a ray that started parallel bends to become collinear with the far focal point. A diverging lens is almost like a converging lens turned inside out. A ray of light that starts off parallel instead bends to become collinear with the near focal point. Of course, it doesn't bounce back, but instead, if you draw out, again, sort of a framework, we draw out this framework here, just make a straight line or take a ruler or something and put it on your page so that it's making a straight line between the near focal point on the side of the object and the point of intersection with the mirror, with the lens, and treat that as the path that light's going to continue on. That path is the direction light's going to travel. So you've got a ray of light that starts parallel and bends to become collinear with the near focal point. Essentially, this is traveling directly away from that near focal point. And likewise, for the converging lens, we had a ray of light that started off from the object towards the near focal point that bent to become parallel. Diverging lens, we've got the exact reverse of that. A ray of light on a path that starts from the object towards the far focal point, but of course is never going to get there because that ray of light from the object going towards the far focal point is going to hit the lens first, which means it's going to bend. And how would you expect that to bend? Yeah, that's going to become parallel. For the converging lens, a ray of light through the near focal point bends to become parallel. For the diverging lens, a ray of light going towards the far focal point bends to become parallel. So we've got these three final principal rays. And of course, there are plenty of other rays as well in all possible directions, but the three principal rays are the easiest ones to draw out. And those are enough because we can clearly see that these rays are not going to intersect on that side. So what do we have to do to find an image? Yeah, if we backtrace all of these, backtrace, 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 they all seem to be coming from this one point. And of course, nothing was actually happening at that point. They just seem to be coming from there. So we would call that a virtual image. And in fact, a diverging lens always creates a virtual image. In the same way that the diverging mirror always creates a virtual image, the diverging lens also always creates a virtual image. And as before, we're going to treat the direction light is traveling at the end as the positive direction. So this is still the positive direction, the direction light's traveling at the end. Since the virtual image is on the opposite side of the lens from the direction light is traveling, we're going to call this a negative distance, a negative value for image distance. And I think that covers all the possibilities. We've got the converging mirror, converging lens, diverging lens. Oh, the diverging lens, by the way, is going to be shaped concave or concave. Like if you make a straight walled sides and then bend them inwards, that's a concave shape, which is going to act as a diverging lens. So again, kind of opposite from mirrors, but they still all follow the same equation. And if you're looking at behavior of light, converging versus diverging, these use the same sign convention. Converging is always a positive focal length, diverging is always a negative focal length. Any other questions on the sign conventions or the behavior of light or anything else like that?
Yeah, really quick. What would be considered a magnifying glass?
Um, well, which one of these led to the image being larger?
The converging, but the image is upside down.
Right, so that's a problem too. You don't want a magnifying glass that makes things upside down. But typically, do you use a magnifying glass to look at something far away or close up?
Close up.
Right, so you put the object closer to the lens inside the focal length and try doing the ray tracing on that. You should end up with a right side up virtual image that's larger than the original object. Whereas a diverging lens doesn't work for that because it does create a right side up image, but it creates one smaller than the object.
Oh, okay. Thank you.
And this is also why, for instance, if you hold up a magnifying glass to look at something far away, it's going to look upside down. And if you hold something closer and closer to the magnifying glass, you eventually get to a point where it suddenly looks really blurry and you can't see anything. That's because the object has just passed through the focal point. So it's actually very easy to find the focal point of a converging lens. Just move the upside down looking object slowly closer and closer until it suddenly looks blurry and then flips to right side up. That one point where it looks blurry is the focal point. Finding the focal point for a diverging lens can be a little trickier because there is no location where everything suddenly vanishes, where there's no image. But there are other ways to find it for that as well. Any other questions on that? All right, then get more practice with this. The more practice you get with ray tracing and working with the equations, the more intuitive this becomes. Ideally, you want to get to a point where you can look at a situation and just immediately say, oh yeah, of course that will create a virtual image. But that's not going to happen immediately. It takes a lot of practice. So practice, practice, practice. Look for connections, look for patterns. Try and develop an intuition for what sorts of situations create what sorts of images and why. Feel free to email me if you have any other questions, and I will see you next time.